Ask one of your questions.
NTC thermoresistor shows that as temperature increases, resistance does what?
This is the thermistor.
Thermistor.
Yeah. Okay, guys. Who wants to answer this one? He says, huh?
I'm just saying, it's an ENTC.
Yeah.
ETC.
And what do you want to know?
What happens to the resistance as temperature goes up, right? On an ETC thermistor.
Cause the resistance temperature to decrease.
Decrease. Is that okay? Good. Okay, so Mitchell can't answer the next one.
Yeah.
Do you have any question you can come up with, Barry? About sensors, huh? Jackson, what you got? You got a question about sensors? Okay. Michael, you're next.
All of these sensors
Here's the question. I didn't hear it. Pick
you.
up.
All of these sensors you.
Are we okay? Is that correct? What's that? Is Hall effect? Hall effect sensor?
Yes. Sensors.
That's okay. That's why we do 5. Y'all gonna answer 3. Y'all gonna ask 3. Ask 3. But y'all got 5. So. Okay, Larry, your turn. Oh, who answered that? I'm doing this wrong. So Mitchell answered the first one. He didn't ask this yet. I'm getting messed up here. So Mitchell answered the first one. And then Larry answered this one. That's all we've asked so far, right?
You put the no X as under the S because they asked
What?
the question.
Yeah, I asked the first
Okay, Larry, your turn to ask a question.
How is the DTC thermistor characterized?
ETC thermistor. So Larry's answered 1, Mitchell answered 1, so it's up to y'all guys.
Extremely large resistance change.
In which
Small
direction?
temperature change.
Huh?
Extremely large resistance change for small temperature change.
Yeah, but which direction? It's a PTC. So as temperature goes up, so we have 2 types of thermistors. We have positive temperature coefficients and we have negative temperature coefficients. Positive temperature coefficients means the resistance changes in the same direction as temperature. Negative means it changes in the opposite direction, right? You understand? So if temperature goes up, and resistance goes up, it's a PTC. If the temperature goes up and resistance goes down, it's a NTC. Can I help you?
Looking for Mr. Scott's welding.
It's in the room next door.
So that's these double doors.
Yeah. Okay, Mitchell, your turn to ask the question.
Okay. In a thermistor, increase in electron hole pairs causes what type of resistance?
That's a good question.
In a thermistor, increase in electron hole pairs causes what type of resistance?
So he's asking if the resistance is going to increase or resistance is going to decrease. Is that correct? Go answer that one. Go. Okay, Bound. Your turn to
What sensor can be used to monitor the level in a tank, detect metallic and non-metallic objects, and detect other objects that easily reflect sound waves?
Somebody's going to have to answer besides my band. She asked the question. So somebody besides my band needs to answer that. She's looking for a sensor that can basically detect metallic and non-metallic objects, including liquids and solids. Huh?
Ultrasound?
Yes.
No. Ultrasonic.
Mhm.
I see where it says,
Oh, I'm sorry, I didn't hear you last part. Yeah. Sound was the trick there. Okay, so Mitch, will you answer that? Huh?
yeah.
Okay, so we roll back around. Joseph, your turn to ask another question.
The light sensor is a transducer. It operates based on the interaction between deformation of certain materials and electrical charge.
An electrical charge.
That's the piezo.
Yeah, electric.
Piezoelectric. What'd you say? What'd you call it, Larry? What'd you call it?
Piezo.
We pronounce piezo. Piezo. Barry, you got a question? About sensors. Jackson, you have a question? Okay, Michael, last one.
What is the function of thermistor in the electrical circuit?
Okay, that's a good question. A thermistor, what's the function of a thermistor in a what?
There's various forms of energy that produces
But a thermistor is not we can't really say various forms of energy because there's a lot of forms of energy that a thermistor would not work with. But it's a certain thermistor, right? So what does the thermistor say? What does the thermistor sense? Temperature, is that correct? Jackson? Huh?
You said, is that correct?
Yeah, I'm asking you. It's your question. You got to know.
Yeah.
Huh?
Yeah, that's right.
Okay. So who answered that one? That was easy. Okay, Michael, your turn.
What is PEL?
What is what, Michael?
PEL,
PDL?
permissible exposure. What is PEL?
You want to know what it measures?
Well, really, everyone else can have, yeah, I can look at
So, y'all hear his question? So a lot of times we can just ask what a sensor actually measures. We got all types of sensors out there, and one of the big things is understanding what they measure. Right? What do they do? What do we use that sensor for? So,
You want to know what a PEL is? What it stands for?
I know he already said what it stands for, so it's got to be what it does. So you can't use what it stands for because
A regulatory limit on the amount of workspace exposure to the hazardous chemical.
they're good. Okay, Larry, your turn.
Okay. Easy. What is a transducer?
What is a transducer? That is a good one. That's an easy one.
A device that you want to know what it is.
What does it do? Yeah. Some,
A device that converts various forms of energy into electrical energy.
okay, that's good. Is that right? I'm sorry. That's a sensor. A transducer is another name for sensor. So, okay, Mitchell. I'll let my man answer that because she needed a question.
A transistor can work below 25.
A transmistor.
Yeah.
Okay.
Can work below 25 degrees Celsius if
That's a pretty specific question. You're probably going to have to look that one up. Is that you call it a transmistor or a thermistor?
thermostat.
Okay. Looks like I don't even know what I don't even know what a transmistor.
Okay, can you repeat your question again?
Thermistor can work below 25 degrees Celsius if
Yeah, that's specific. I don't know that one. They'll
It's
go.
simple. It's real simple.
One more time, repeat the question.
Okay. A thermistor can work below 25 degrees Celsius if
If it's cold resistance measured at 25 or room temperature? No.
as a part. But you just said read it all the way through. We'll pick it up. It's really one word that will take you.
However, some manufacturers.
There you go.
Manufacturers.
If
Okay.
it's manufactured to.
Specific lower temperatures. Okay.
Okay, but
But
you don't-
normally they are.
that's three. You don't answer anymore.
Oh,
Normally it's.
Okay, but about answer one of your questions.
okay. This is a true or false question.
True or false? 50-50. 50-50, guys.
The input of a Hall generator depends on the presence of a magnetic field and the current flow in the Hall generator. Is it true or false?
False.
It's false.
Uh-oh.
The output, not the input, but
Not
it's
the output. The output depends on that. You got to listen to the questions. Yeah. Okay, Joe. Last question.
Name two uses for all effect sensors.
Two uses for Hall effect sensor.
Magnetic card reader.
What, Michael? You got it right.
Yeah.
Oh, his answer? Everybody hear his answer? Say it out. Say it again, Michael.
A magnetic card reader or temperature.
Yeah, it's got a lot of uses. I mean, a lot of uses.
Yeah.
Odds are, if you got a tachometer on your car, it's probably a Hall effect sensor in your transmission. So they're used to sense speed. They're used to sense all kind of different things. Okay, Jackson. Barry, you got a question?
Yeah, I got this true or false question.
That's fine.
This is true or false. Every transducer has a signal. I mean, has a sensor. But every sensor is a transducer.
So every transducer is a sensor. There's every sensor of transducer.
Yes or no? You said that they do, they don't need,
False.
do they need transducer? They need transducer. Every transducer has to have a signal. I mean, has to have a system.
Yeah, but every sensor doesn't have. Yeah, we got limit switches. Those wouldn't be considered transducers because they're mechanical. So normally electromechanical sensors are not considered to be transducers. They got to be. We okay, Barry? You look good.
When the temperature.
Wait. Who answered that one?
Larry,
Larry answered. Okay, Larry, you hit your limit. Okay, Jackson, your turn.
When the temperature increases in a NTC thermistor, what happens to the resistance? Did we already ask that one?
Yeah, we've already asked that.
True or false? It increases. Does it increase? Is it, the question was true. I said it increases.
You got another question, Jackson?
What is the difference between PTC and NTC thermistor?
What's the difference between an NTC and a PTC thermistor? I'm asking a bunch of questions about thermistors. That's okay. You can't just say one's negative, one's positive.
Well, that's true. I mean, yeah.
I mean, that's a.
Yeah, it's not.
So a thermistor. Wait. Nobody's answered this one yet. So what's the difference between difference between a NTC and a PTC thermistor? You can't say one's negative and one's positive, which is what Joey answered, because that's not true.
So
The answer. Okay, awesome.
PTC, they decrease the resistance as the temperature is increased. But PTC, since they're made at a high positive temperature coefficient,
So
increases the resistance.
Jackson had to answer his own question.
Both of them use temperature to increase or decrease.
Yep, he's already gave the answer. He already gave the answers.
I didn't want to waste time.
Yeah, it's in his name, thermistor, right? A resistor that changes its temperature with what? Changes its resistance with temperature. One of them is a positive temperature coefficient. One of them is a negative temperature coefficient. So which one would go up if the temperature goes up, the resistance goes up? A positive. And the other one, the resistance will go down if the temperature goes up. Most of your thermistors are NTCs. All the thermistors that we have that I'll show y'all in class are NTCs. So that means when they get warm, their resistance goes down. Okay, Michael, your turn.
What are the two basic operating modes of ultrasonic sensor?
Oh, two basic operating modes. The two basic operating modes of an ultrasonic sensor. So Joey, you need one. Barry, you need one. Huh? Yeah, with ultrasonic sensor.
Oh, direct mode and diffusion mode.
Okay, direct mode and diffuse mode, is that okay? So we use you can use them to find if you can use them to find if a object is there or not there. And you can also use them to check distance, right? So we have one of these on our Amatro line over there. Okay, Larry, your turn.
What is the transducer that detects radioactive materials?
Okay.
That's what I got.
Okay, Mitchell, your turn.
Oh, this is kind of like a two-part question.
That's that moment.
For
And did you-
NTC.
Is, is thermistor the first part of the chapter? or something?
Yes, the first part. NTC thermistor to measure flow. How many does it take, and what position should they be in?
A thermistor to measure flow.
And the position that it's in.
I don't know the answer to that one. A thermistor to measure flow.
How many, and their positions in the flow.
So you got to send it through something else.
Just say it's in the, you got two of them.
Thermistors.
Yeah.
Temperature sensors to measure flow. I know we can use pressure sensors to measure flow, but we have to send it through some type of obstruction. So you have a high pressure side and a low pressure side. The temperature, I don't know. Tell us the answer to that.
It takes,
Huh?
it takes two of them.
I figured two because that's how many pressure sensor it takes. But
It's on page 197.
I'm looking at it.
And there's one that's kind of like sits not in direct flow, and the other one is sit in the flow, and it takes the motion of the flow, creates a temperature, and the other one, since it's in a stable flow, it takes, and they compare each, the difference between both of them.
Yeah, it says in the
Never heard.
the amount of flow in the circuit determines how rapidly heat is conducted in NTC current. Rapid flow dissipates heat rapidly, less flow dissipates heat. So the longer flow, there's more resistance in the signal.
So we have what we call laminar flow, which is flow in one direction, and what do they call the other one, which has a bunch of friction. So it's moving faster in the middle of the pipe than it is on the sides, because the sides it's actually rubbing against the sides of the flow. Yeah, opposition. What he says we're using them is that we're using them to measure temperature. But what we have to do is we have to use the same type on both sides, and we have to run current through them. So if they run current through them, they're going to get hot. This is one of the problems that the thermistor has with measuring temperature because they're a resistor. So how are we going to sense How are we going to sense temperature with a resistor?
But I guess having two of them.
No, well, how are we going to you're talking about flow. I'm just talking about basically what we need to do with a thermistor. So thermistors are not linear for several reasons, but one reason is that if I was to come over and have a thermistor, and then I come over and put it across a DC source, how am I going to measure temperature? How am I going to convert this over to a temperature? Okay, so this is 12 volts. If I come over and put a voltmeter across here, this is going to be 12 volts. It's going to be 12 volts at 15 degrees centigrade. It's going to be 12 volts because it's the only element in a series circuit. If it's the only element in a series circuit, it's going to drop the entire voltage no matter what. So we got one of two options. The only other option we got is to use an ammeter. Ammeters we don't use that much. Well, normally what we do is we put a fixed resistor that I know the size of, and then I put the thermistor in series with it. Now I've got 12 volts. This 12 volts is going to be distributed across the two resistors, right? You understand that? So if this is an NTC thermistor, when the temperature goes up, its resistance goes down, then the voltage drop across the thermistor would go down. Well, it's working like a rheostat, not like a pot. But you're not controlling the rheostat with a knob. You're controlling the resistance with temperature. Now the problem is when you put current flow through a thermistor, now we got power, which in this would be heat because it's a resistor is equal to I times R. I understand that. So the thermistor actually gets warm itself. So this is the principle they're using here. They're using how fast the thermistor cools off, right? So they put current through it. The current is going to create a what? A power. The power is going to create heat, which if it's an NTC thermistor, it'll cause its resistance to go down. Now what's going to happen when the water flows on it, it's going to do what? It's going to cool off, causing the resistance to go back up. Well, we got to use two of them, right? You understand that? So one of them's in the laminar flow, one of them's in the center where it's getting all the flow, so it's going to cool down faster. The other one is up in the resistive flow, which is up against the side, so it's going to cool off slower because the water's moving slower. I guess they could do it that way, but that's the first time I've heard of that. But it makes sense. I've never seen a flow meter that works off thermistors, but undoubtedly it's out there because it's in the book. But you can see how that works. So what we'd have to do is we'd have to have two together, and then we have to compare the distance. Usually flow meters they'll put an impeller in here. So it's nothing but a propeller, and then they'll have a magnet on one side, and on the other side of the tube they'll have a Hall effect sensor, and it gets a pulse every time the blade flies around there. Another way we can do it is send it through a Ventura, which is just a compression, and then we put a pressure sensor right here, and then we put a pressure sensor right there. Of course, the faster it flows through that, it creates low pressure, just like airplanes fly, you know. So you'd have a high pressure side here, you'd have a low pressure side right there. And the difference between those pressure would be proportional to the what? To the flow. So there's several ways we can measure. They got one called a vane too, where they actually put a little vane in here. And then it's got a calibrated spring on it. And then when the flow moves against it, it does what? It pushes that little vane out of the way. How far it pushes depends on the tension on the spring. And they can measure that deflection. They usually hook a potentiometer up to that thing, which is pretty neat. But I have never seen them use a thermistor to measure the flow. So did anybody get credit for that one? Barry, you answer that one?
Yeah, this question?
Uh-huh. About the thermistors?
He said he had a guess.
Oh, you have a guess? Let's move on then.
Mike got it.
Huh? Well, they've already got 3. We don't go past 3, so. Okay, Bavana, you got a question?
Okay, this one have 2 answers. It says,
Don't be about, is it about thermistors? Okay.
I only have one question about the mission. Blank and blank are available from manufacturers that can be used to make specific calculations.
Ooh.
Specific calculations.
Blank and blank are available from manufacturers that can be used to make specific calculations.
What is she asking about is the test equipment that we use to measure, probably measure the output of a sensor.
Blank and blank are available from manufacturers that can be used to make specific calculations.
I don't know how the book could do that. There's all kind of stuff that does that. I'm trying to find it in the book.
Yes, no.
Might be. Okay, well, better go ahead and answer your question.
Formulas and tables.
Formulas and tables. Okay, Barry, you got a question? Yes, you should have. I agree with you. Yeah, I agree with you, but that's okay.
What's the difference between actuator and system? It's a 2-part question.
What's the difference between an actuator and a system?
Sensor.
A sensor. Oh, okay. That's a good question. Okay, Barry, give us the answer.
Basically, physically they can be the same thing. One is input into a system, one is output from the system. So it's like you got some headphones. You can use it as a microphone. You have a microphone. It's like a headphone and microphone. You know, sometimes you can record yourself through your headphones.
An actuator is a device that takes a power source and converts it into motion. That's what an actuator does. I'm telling you what an actuator does. An actuator takes a power source and converts it into a motion. So a speaker would be an actuator. Okay, because it's taking current and converting it into sound. But it's doing that by emotion, right? A sensor senses. A sensor takes takes a physical quantity and converts it into an electrical quantity. So basically, they're kind of opposite of each other, but they're not actually that. Huh? Well, they're not the opposite because I've got this output right here. This would not be an actuator, but it would be an output. But it's got sensors on it, so I can come up here and touch this. It's got a sensor on it. By the way, we have different types of sensors we put on this. the stuff that you can touch with your finger or touch with anything, and it responds. Those are resistive sensors. Normally, we don't do that on like tablets and stuff like that because you'd be touching them all the time. So mostly these guys these are capacitive sensors right here. So this is just a bunch of capacitors, which nobody asked about about capacitive sensors. So capacitive sensors can sense both liquids and solids, right? So this is nothing but thousands of capacitive sensors on my display. But an actuator is a device that takes what? Electrical energy and converts it over to motion, physical energy. So this right here would be a sensor. But this right here is not an actuator. This is not an actuator. Because to get an actuator, we have to do what? We have to create motion. So I guess you could say, it's when you use the term output. So technically, probably you were right, because one of them takes physical and converts it over to the electrical. The other one takes electrical and converts it over to what? Physical. So it is right. But an output does not have to be physical. Okay, Jackson, you got a question? Huh? You got another question, Barry? Huh? Go ahead.
It's the same question. It's like, how you do the IQ test. It'd be like, an actuator is to a sensor as a cat is to a dog. Hands are to feet. Resistors are diodes. TE is to a motor.
So what are you asking? A sensor is to an actuator. Everybody got that same question? What are you asking, Barry?
Need the analogy.
Huh?
Like you know.
So you're saying a sensor is to an
What's the
actuator?
relationship between
A sensor and actuator. Of course, we've already answered that.
That was my other question. You already answered.
So guys, what does a sensor do? You just can't.
It's a device that detects and measures a visual properly and records and has otherwise responsible.
That sounds like a good reading. We need to understand what a sensor does. The basic function of a sensor. What is my sensor? We got 5 senses. What do those senses do? My brain has nothing to know. My brain does not know touch. My brain does not process touch. What does my brain process? What? But how's it sent? Yeah, your brain is an electrical device. Y'all understand? It sends out electrical pulses to cause muscles to contract and retract. It receives electrical information from your neurons or up your nerve cells into the brain. So your brain processes electrical information. It stores stuff with electrical information. You know, so what does my sensors do? I got 5 senses. I've got sight. I've got what? Smell. I've got hearing. I've got touch. Is that all? Okay. So what does my sensor do? So I come up here and I touch something. What does those nerves do? It converts a physical quantity into a what? In its electrical equivalent. That's what what do sensors do in electricity? They take physical quantities and convert them into electrical signals. And then that's what we process. We don't process heat. We don't process smell. We don't process touch, your brain processes electrical signals. So that's what your nerves do. We call them neurons, right? What do they do? You come in, you touch something. What did it just do? It took that quantity, converted it over to electrical impulses. These went flying up through my nerves, right, in my brain, and my brain processed that for me and says, okay, Rich, you're touching the top of that, right? I'm sitting here looking, right? You understand? Then I've got these receptors back there, right? The rods and cones that do what? Takes that and converts it over to electrical signals, sends it up my optic nerves to my brain, and my brain processes electrical signals. So that's what a sensor does. So somehow we got to take a physical quantity and convert it into what? An electrical signal. Now that I've got it in an electrical signal, I can put it up on an indicator, right? You understand that? I can do what? So when I put my meter into my circuit, you're putting a sensor in there. But it comes up there, measures those difference in potentials, right? And does what? Then we have electrical signals, and it comes up and we can process them. So what does the sensor do? So it takes a physical quantity and converts it over to an electrical signal, right? And now we got it in an electrical signal, what can we do with electricity? Well, good gracious, if it's DC, we can control it electronically. We can sense it electronically. We can take it into a computer. So now I can take it into a computer. So I'm up here writing on this. My computer has no idea what I'm doing, right? You understand? What am I doing? Well, I'm running this into a what? Into a sensor. And what does a sensor do? What does the sensor do? It's converting a physical quantity into an electrical quantity. And then once it's got it into an electrical quantity, it can be processed. We can do something to it, right? You understand that? Because we have all these different types of stuff that we can control electrically. So that's what a transducer is. That's what a sensor is. A sensor is going to be a device that takes a physical quantity and converts it into electrical quantity. So once it's done that way, I can process it. I can process it electrically, or I can process it electronically. All the sensors that they show here are going to be processed electronically. And then we have specialized computers that are basically designed to do this. We call them PLCs, right? Programmable logic controller. Some of you are taking that class this term. So a PLC is specifically, that's what it does. It takes these sensors, whether they be push buttons, mechanical push buttons, or whatever, and it does what? It converts it over to an electrical quantity, so now I can process it with a computer. So you're seeing me doing that right there right now. This is a sensor. That right there is a sensor. That's what we call it, a microphone. What's the microphone do? I'm not talking in electricity. I'm talking in sound waves. So what does it do? Well, it sits in sound waves, right? You understand? And then what does it do? It takes that sound wave and converts it over to an electrical quantity, so we can do what? We can process it. We can save it. Now that it's electricity, we have the ability to record it, right? And all kinds of neat stuff. So guys, that's what sensors do. That's what they're functioning in life. And they do exactly, so electrical sensors do exactly the same thing that your senses do. Which is pretty neat. And then I've got all these actuators, these muscles. So that's basically what we're doing. So I'm taking sensors and then I'm bringing it into my brain and processing those senses. And then what's it doing? It's making decisions and sending out electrical pulses so my muscles move. So right now I'm talking and all I'm doing is my brain is just moving a bunch of what? Just moving a bunch of muscles. And then I'm blowing air over a vocal cord which vibrates, right, which is still, and it causes me to send out sound waves. So what kind of sensors did did this chapter talk about?
All the gas detectors.
Yeah, I talked about thermistors. So guys, let's just go back. Let's drop back in this. What's some of the things we want to sense? Of course, most of y'all chose this one.
Temperature.
What's some of the things we might? What's some of the other things we might want to sense?
Flow.
Using sensors.
Mitchell said flow. The rate something's moving. Usually flow, we talk about a fluid, right? What'd you say, Barry?
So, things we might want to do.
Sense. In motion, yeah. I've got motion detectors on the back of my house. So I just go truck it out. In fact, my front porch light has a motion detector on it. So I just walk up on my porch and the dang light comes on right at night, so I don't have to fiddle around and trying to get my keys in the door.
Distance.
Yeah, distance for sure. Anything else?
So, how do they sense weight?
Weight. We have different ways we can sense weight. Now this is kind of loaded. This could also be a force, which is what weight is, right? You understand? And then of course, pressure and force are two different things. Anybody know the difference between a pressure and a force? What's a force? So force is a something that tries to cause something to change direction. A pressure is what's actually doing the pushing that creates the force. So we can't have force unless we have a what? A pressure. Anything else? So weight, force, pressure, those are. I was going up to my granddaughter. She goes up to the University of North Alabama. And she got up to Warrior and had a flat tire. She's got one of those SUVs where you got to have that special tool to stick in there to lower the tire, and she didn't have that. So here she was up there. And I was cruising up there, and I decided I didn't want to use my gas pedal anymore, so I engaged something called a cruise control. So what was my cruise control sensing? Starts off with an S, guys. Speed, yeah, we definitely got to set speed. We set speed all the time. If I'm running a process line, especially like down at Mercedes or something, we want the line to run at the same speed, right? You understand that? So we're constantly sensing the speed of the line. I think Larry said they decided to speed up a section or slow down a section while they was learning something, and nobody else knew that. So it was a mess down there for a little while. So temperature, flow, position, motion, weight, force, pressure, speed, anything else y'all can think of we might want to see? Yeah. I don't know if I'm going to sense that or not. We had sensors that sense that. We had we had what they call gauges where they check the gauge. So if they put a coating on anything, they want to make sure the gauge is perfect. Well, what they do is they use an X-ray machine, and the X-ray machine actually measures the thickness of the coat that they put on there, which is pretty good. So yeah, they have those gauges. Yeah, we definitely want to sense gas. A lot of people have this in their house now, CO2 sensors in their house, especially if you got a gas heater. You probably need to have one of those in your house. Anything else?
City light.
Sure, we can sense light. Yeah, my motion detectors don't work during the day. They only work at what? Night. A lot of people have floodlights that only come on at night. All these lights out here in the parking lot only come on at night. Well, how do they do that? Well, they sense what? Sense light. Before they figured out how to do that, all your lights were on timers. And the problem is they had to adjust the timers all the time, or they'd be in the summertime and the lights would be coming on at 5 o'clock, right? You understand? But they don't do that now. All the street lights out here on the highway come on. They only come on at what? Night. So they got light sensors on. Anything else?
Voltage.
Yeah, we can sense the voltage. Of course, if we set a voltage, we probably need to sense what? Current. Anything else? Yeah, sound, process. And there's a perfect example right there. That's a microphone, right? You understand what's it sensing? It's sensing sound. Anything else? Probably need to sense this too. Where something's at. We're constantly sensing the position, right? We have two types. Then we have something called proximity. Anybody know the difference between a position sensor and a proximity sensor? Well, position is where it's at within a space, right? Proximity means next to. We have a bunch of proximity sensors because that's all we want to do is want to know when it's at a spot. We don't care where it's at till it gets there, and we don't care where it's at when it leaves. Anymore? I mean, there's all kind of stuff, you know. We might want to sense what? Color. We might want to sense. Anybody in here an avid fisherman? Most people that do are very avid fishermen. Well, they check the water out all the time. And not only check temperature, but they check the pH, right? Different fish body different pHs, and they can figure out where they're at. Huh? Yeah, if you got an aquarium, monitor to the pH too. What is pH? Well, it's the ratio between the acid and the bases. So if you get if you have a high pH, that means you got a lot of acid in there, and you got to do what? You got to lower it because your fish don't like a lot of pH. Salinity is how much salt it's got in it.
Specific gravity.
Yeah, but I forgot about the fish aquarium checking the pH. Yeah, you can definitely kill your fish if you don't monitor the pH. Swimming pools too. If you've ever been in swimming pools, you monitor the pH. If you don't have it right, if you get too much acid in there, then it's going to burn everybody's eyes and it's going to turn their swimsuits white. If you get too low pH, then you're going to get mildew and all kind of stuff or going in your pool. Kind of like when you set it up during the winter time. Okay, anything else, guys? I mean, good gracious. Color, light, would be color, a sense of color. What else? Well, that would be a form of light. We have different types of wavelengths or something to detect light, you know. Like most remotes use infrared. Anything else, guys? But we could go on. I mean, we could sense all kinds of different things. And odds are there's probably a sensor out there that gives us the ability to sense just about anything we want to.
See the video. They have
where they made something that like so machines can taste for you now. They can tell if it's like sour, if it's bitter, sweet.
Well, that would be the pH. That would be pH, and that's what you're basically sensing there, which would be pretty neat. But we can sense. We got size in there. No, I didn't put. Definitely sense size. They're constantly doing that. So we got sensors over on their line that senses if it's the wrong size, and then if it's the wrong size, then what they do? Hopefully, we're going to reject it. So we got all types of sensors